All right.
We're on the air.
Okay, we're live. I'm told we're live. Welcome, everybody. Welcome to the March meeting of the Ottawa chapter RASC. I am Mike Mogadam. No, I'm not. I have a strange sense of deja vu, but a different time and place. Anyway, Mike unfortunately had a commitment that kept him from coming tonight, so he twisted my arm, and he had to twist really hard and asked me to chair the meeting tonight, so you'll have to bear with me tonight. So welcome everybody. I'm glad you could all come out and find a parking spot. I know we had a little bit of a a problem with that, but looks like we got a pretty full house. There are not too many empty seats there, so I'm glad you could all make it tonight, and even though it's cold and still winter. So we have got a really interesting program for you tonight. We have an excellent speaker that I think you're going to find very, very interesting. We have some very cool imagery that's been done. And you'll probably never guess what object in the last couple of months, but very cool imagery. And so yes, you'll have to bear with me since I'm just kind of jumping into this. I may be a little bit disorganized, but as I said, bear with me. I think we're good for the next meeting there. So tonight, as I mentioned, we have Dr. Haley Sapers. She's going to talk to us about astrobiology. Yeah, I see some nods there. Yeah, I think you're going to find this really interesting. So she's got a really good talk for us. Then we're going to have our break, and followed up by observations, announcements, and we have a whack of door prizes tonight. So stick with us. I think you'll like this. All right. So just to give you a little bit of background, because unfortunately we had some other scheduling conflicts there, and so we don't have some of our regular segments there, our monthly summaries and our 10 minutes from Al Scott there. Unfortunately, those folks couldn't join us there. So I just wanted to mention for any people here for the first time, any new members? Oh my goodness! Oh, that's way cool. Hey, I know you. Well, that's good. I'm glad to see that you guys could come. I hope you enjoy our program. Be aware this is a little different than what we usually do, but you'll get the general gist, and you're in some good company there. So feel free to mingle at the break and afterwards, and I think you'll enjoy your time here. But just to give, for those folks that are new, just want to give you a little bit of a sampling of what we do here at the RASC. Obviously, you can see from our map that we have centers all across the country, a heavy concentration here in Ontario. Currently, we're at 28 centers? 28 centers across the country.
Charlottetown's closing.
Sorry?
Charlottetown Center's closing.
We were 29, we're now 28.
Charlottetown's closing, that's a shame.
They fight members.
Yeah.
Oh, yeah, and not a lot of clear skies, I guess, eh? Well, those members can dial into our meeting thanks to our esteemed videographer there. So, but you can see we are an active center. We have Ottawa Center is the second largest in the club, in the national organization, second only to Toronto. And I think currently we have something like 2,000? Is it 2,000 members active? 2,500. So it's a pretty big organization there, and we share things across centers there. I know since we started broadcasting our meetings, people from other centers have made a point of tuning in and seeing our broadcasts there, and very enamored by what we do here. So we like to be on the edge there and show different things. All right, so Ottawa Center, and oh yes, thank you for adding that. I didn't know we were going to add that. As I'm sure most, if not all of you are aware, Mr. Spock passed away. Yeah, Leonard Nimoy just passed away. Now, I was really surprised by that because I thought Vulcans lived for about 200 years.
Half-breed.
Yeah, is that what it was? Yeah. Well, that and smoking apparently. Yeah, smoking did him in too there. I didn't think Vulcans smoked it, but again, it's that human influence, eh? Yeah. Thanks for that, Tim. Appreciate that. So I'm sad to hear that because I certainly grew up with Star Trek and the movie, the series and the movies. So Leonard, wherever you are, live long and prosper. All right, next. Yeah, I know. Well, in the next life, right? So we have 9 new members already in 2015, including 2 new members there. Krista and Mike, are you amongst us here tonight? Couldn't make it out? Okay. So yes, welcome 2 new members. Oh yes, and Mr. Eric LeMay, he's a new member too. I know that guy from somewhere. Yeah. Awesome. Good show, Eric. All right, and for those of you who haven't received your membership cards yet, is Art here tonight with us? Yes, so Art may have some of the membership cards available for you in the theater foyer at break time. Okay? All right. Enough of the preliminaries. I've been waiting for this talk ever since I heard it was going to happen. So Dr. Haley Sapers is a PhD, and I could spend probably the next 15 minutes going over her resume. It's very impressive. This gal has been in a lot of places and has done a lot of things, so I'm really looking forward to the talk. Just to give you a really quick summary though, she is currently a postdoctoral fellow at the Center for Planetary Sciences and Exploration at Western University. She's also an associate research scientist with the Planetary Science Institute down in Tucson, Arizona. I guess you spend the warm time in Arizona and the cold time. Yeah, okay. And from 2012 to last year, 2014, she was a postdoctoral fellow at the Canadian Astrobiology Canadian Astrobiology Training Program at McGill University. So some very impressive credentials there. She did her PhD in geology, specializing in planetary sciences at University of Western Ontario. And she was actually a student of Carleton University here, so yeah, a hometown girl. Excellent. So without me blathering on further, I'd really like to introduce you to Dr. Haley Sapers. Come on down. So there's a pointer if you need one. I just want to ask you quickly, I've been accused sometimes of having alien blood in my veins, and it hurts when I do that. Do you have it?
Probably shouldn't do that.
I shouldn't do that? Oh, see, I told you she was good.
Thank you very much.
Take it away.
Hi, thank you very much for all coming tonight, and I would like to extend my thanks to Mike for the invitation and the opportunity to come and speak. So I'm an astrobiologist at Western University right now, where I'm studying biosignatures, or the traces that life leaves behind for us to find. So I'm going to talk this evening about some of my research that I'm doing, as well as what astrobiology is and why it is so hard to define life, and how do we look for something that we can't really define if we don't have a good idea of what life really is.
Thank you.
So I'm sure a lot of people spend a great deal of time looking up into the sky in the evening and looking up at the stars and wondering what they hold and what's out there. But how many of you actually spend time looking between the stars, looking at the darkness, the emptiness, and wondering what's there where we can't see, what's between the lines? And so that's exactly what Hubble did. I'm sure a lot of you are familiar with the Hubble Ultra Deep Field and the Hubble Extreme Deep Field. And the Hubble Ultra Extreme Deep Field took about 10 years of Hubble photographs from the center of the Hubble Ultra Deep Field, and about 5,500 galaxies that were imaged. And those galaxies in that image are 1/10 of the brightness of what the human eye can see. So this is about 2 million seconds of collection from about 2,000 images, and it gets back to about 13.2 billion years. You're looking into the past through this image. So what I like about this image is that it tells us that almost every point of light in this image is an entire galaxy. And each of those galaxies has millions and billions of stars, and each one of those stars likely has its own planetary system. So there are billions of planets out there. And what we know about Earth and our solar system is very likely that those planets also harbor life. And I like to think that the proof for life beyond Earth is that there's life here on Earth. So just to give you an idea, just to put that into perspective, those billions of stars and billions of planets are on an area in your field of view when you're looking out into the sky. It's an area smaller than your thumb stretched out at arm's length. You can blot out billions and billions of potential planets with your thumb in the evening. So I want to ask you a question now, thinking to all those billions of planets and the fact that there's probably life on them, or there was life on them, and how do we define life? What are we even looking for? So with these pictures, which of the following items do you think is alive? We have bacterial spores that are neither growing nor dividing. We have a virus. It's made of biological material. It's biologically active. Here we have kaolinite. It's a clay mineral. It carries information and it self-replicates on a template. We have fire. Fire grows, it consumes energy. So which one of those things would you consider to be alive, and why? Well, there really is no consensus. There is no absolute definition or statement that encompasses all that life is. Life is clearly more than the sum of its parts. But we can't really put our finger on what that is, what constitutes being alive, what makes life life. So if we don't know what we're looking for, if we can't define it, what then are we searching for when we look out into those images and we send rovers to Mars, starting with the Viking missions? What is it that we're looking for when we say we're trying to find life on other planets or evidence of life elsewhere in the solar system? And that's where the study of astrobiology comes in. So astrobiology is defined as the study of the origin, evolution, and distribution of life in the universe. We ask some pretty broad questions that can often become somewhat rhetorical and philosophical. So astrobiology is the study of the origins, evolutions, distributions, and the future of life in the universe. So it's going beyond Earth, but also looking at life on Earth, life on early Earth, life in extreme environments on Earth, and life in potential analogs for other planets, and what it means to look for life, what life is. So why is it so hard to define life? Any 5-year-old child can tell you the difference between a family pet and a favorite stuffed animal. So why can the scientific community not make that distinction? Why is it so difficult to come up with a concept or a definition that encompasses what life is? Why is it so difficult to interpret potential evidence of life? Why is there still a debate over the signs of life and even life on early Earth? We can't even make those types of decisions. So a definition should become the notion of life itself. It should encompass all that life is with no ifs, ands, or buts. Definition of life that is more effectively and precisely capturing the fundamental essence of what it means to be alive. So what are the limitations of a definition? Why can't we arrive at one? This is an article I often like to cite and I often like to talk about that was published in Astrobiology that kind of brings up some of the main issues and problems with arriving at a definition for life. So here are the two main definition limitations. Life being defined by undefined terms, which isn't particularly helpful, or where a combination or a list of life's characteristics are used as a definition. A shopping list is not a definition. A shopping list does not make a pie. So some of the definitions that are thrown around use words like complexity or information or self-organized. There is no meaning to those terms. Those terms are inherently meaningless when pulled out of context. They require definitions themselves. What is complexity versus simplicity? What is information? Does information have to be stored or carried or processed? And what is self-organization? What is meant by that term? So we look at these and we think, okay, what about NASA? I mean, that's kind of one of the biggest organizations that studies the beyond. Can NASA come up with a better definition for life? No. I mean, NASA uses the term self-organization. In it itself is an undefined term. So going beyond that, we have tautologies. So you can't say life is a process of living organisms, or this is alive because it's life, or something is life because it's living. I mean, that's a pretty circular argument there. So here again, life is a self-sustained chemical system of undergoing Darwinian evolution. So NASA really doesn't do any better in defining life. What does self-sustained really mean? So another thing is we like to try to define life by taking a human-centric approach. We define life using ideas and values that we see as being important. So life is a way of capturing and using energy and materials. Living things are peculiar aggregates of ordinary material. So these are ideas that we encompass, and they might not necessarily be applicable outside Earth. It's all within our memory, our expectations, and our experience. And then again, we get to the shopping lists. And the problem is that there's no one shopping list. I mean, you can have energy and growth and adaptation, you can have individuality, you can have self-sustaining, you can have evolution, self-replication, low entropy, organization. The problem is if you include all of these terms, you end up with a definition that's too inclusive, and you end up missing things like those bacterial spores. But if you only use some of those terms, you end up including things like fire. So there's no real one recipe for life. There's no one list of characteristics that inclusively defines life. And can we use these definitions literally? Not really, because an organism can be alive even if it's not growing or reproducing or evolving. These little guys are affectionately known as water bears or tardigrades, and they can go into periods of complete stasis until so comes a time where it's warm and sunny again. It goes beyond hibernation. They're not actively undergoing any biological process. Yet, during those periods of stasis, we would still consider them living organisms. So what is life? And what are we looking for? When Curiosity landed on Mars through nail-biting 7 minutes of terror from that sky crane, what were we hoping to find? What did we find in Gale crater? And how do we interpret that evidence? So this is where astrobiology comes in, and astrobiology is really an interdisciplinary science. So I use aspects of biology and geology, of chemistry and physics into these interdisciplinary subjects such as geobiology and geochemistry and biochemistry. So when we're thinking about life, we think about the origin of life, and then we think about habitat creation and colonization. So once life evolves on Earth, it has to colonize Earth. It has to colonize a specific environment. But then how do we know if it's colonized an environment? So if we go to Mars, how do we know there's been an origin of life and then habitat that was able to be colonized by life? Well, that's when we go into preservation. So the origin of life and habitat and colonization goes into habitability. Is the planet habitable? Can life exist there? Can life as we know it grow and evolve? And then through colonization and preservation, we end up with biosignatures. We end up with the footprints that life leaves behind. And with preservation and the origin of life, we look at things like evolution. So both on the early Earth and beyond Earth, we use these principles and these overlaps to be able to understand what we're looking at and evaluate these signatures and evaluate the potential evidence for life in a kind of a global context. So if you're a kid at school and you go out into the playground at recess, and there's going to be footprints in the sand at the playground, there's going to be a whole bunch of rocks in the sand and clumps of sand, and then the bell rings and you all go inside, and you've got footprints and you've got clumps of rocks and holes. And it's pretty easy to tell the difference. It's pretty easy to say, okay, a human made those footprints. That is a biosignature. That was made by somebody that was alive, and it records a biological process of walking, of locomotion. But then you have all of those rocks, and it's pretty easy to say, okay, well, those divots in the sand and those holes in the sand, those were made by rocks. That does not record a biological process. That does not record a life phenomena. That's completely abiotic. But by the end of the day, you end up with something that looks like this. And it becomes really, really difficult to differentiate between a biological signature and an abiotic signature. Something that was created by a living organism and recording life actions, and something that was created by something that was non-living, by something that was abiotic, and is simply recording the geochemical and physical conditions of that environment. It becomes very difficult to pull those apart. So one idea, one paradigm is that we'll know it when we see it. When we see life on another planet, we'll know it. And that brings me to this. Is this image familiar to anybody? So this created a storm of controversy. A lot of people thought that this was evidence of life on Mars. So this is an image, an electron microscope image of a Martian meteorite. And that little guy there in the center, well, thought that it could be a microfossil. And then a lot of people said, well, no, it's way, way, way too small to be a microfossil. Maybe it's a nanofossil, maybe it's something else entirely. The jury's still out. I think the consensus now is that this is completely abiotic. This has nothing to do with life. So the moral of the story here is, if we know it when we see it, we need to know what we're seeing. And we need to be able to have some consensus, some idea about what life is, to be able to interpret those ambiguous signatures, or when we get something back from Mars, or when we get the data from the rovers that are on Mars. How do we interpret that evidence? What is life? I'd like to introduce a bit of a metaphor here. How would you define music?
Sorry, bear with me for a second. We knew this might happen.
So how would one define music? So I think we would all agree that that's music. Yeah, we'd all agree, we'd come to a consensus there that what we just heard is music. Well, actually, it's information that's transmitted through sound waves that our ears detect and our brain interprets as music. That's music. So is that. And that. And that. So maybe it's not so easy to define music. What about this piece? Does that sound like music? Yeah? Well, when it was first played, there were riots in the street because the people of the time didn't believe that was music. That was the rite of spring. There were riots because it was just noise. It did not conform to the idea of what music was. And so the idea of music is constantly evolving as our society evolves, as our body of knowledge evolves, and so is the idea of what life is. As we learn more about it, as we branch out into the extremes, as we realize that there are microorganisms that live and divide and, below 0 degrees Celsius or in deep sea hydrothermal vents or kilometers down under the Earth's surface, we're continually broadening our ideas of life. What about this piece of music?
Yes, yes. Silence is
I see some of you nodding. That was an actual recording of John Cage's piece 433. It was 4 minutes and 33 seconds of silence. And the composer, John Cage, his idea was that music is the sound and the noise all around us. So the idea of music, maybe at the beginning you thought that it had an intrinsic idea, or it would be easy to define or know. But it's really not that simple. And so it's the same with life. When does a collection of notes, of sounds, of ideas, of information become a piece of music? When then does a list of characteristics of processes become a living organism? And brings us back to that question, what is life? So this is a paper, and the authors of the paper try to define life. And really, the only thing that's important in this paper is the last sentence. We lack a definition of life, but one should not forget that in science it may happen that the most interesting questions are precisely those that cannot be answered. So here's an entire paper devoted to trying to define life, and their conclusion is that we can't. So how do we ask questions when they can't be answered? If astrobiology is a scientific pursuit, then it must be driven by hypothesis-based questions. And it brings us back to recess time, where you have all those kids and the footprints and the rocks, and how do you weed out what were footprints made by living organisms and what are holes in the sand made by rocks. And this is the idea of biogenicity. So biogenicity is what makes something, some signature, what makes a footprint interpreted as something that was made by a living organism. So we have a footprint. We have our feature of interest. We have that little, bleb on that Martian meteorite. When do we say it's life? When do we say it's not life? Okay, we say, it looks like life. All right. If life is expected, such as on the Earth, then yeah, we'll say, sure, looks like life, it probably is life. If life is unexpected, such on the moon, no, okay, it looks like life, but we know that it can't be, so it's not. But what happens when we don't have one of those clear null hypotheses, where life is neither expected nor unexpected? We just don't know. And so this brings us into our definite definitions, or our limitations, when we just don't know. So think about trying to define water. You could say water is wet, you could say water is thirst quenching, you could list its properties, it boils at 100 degrees, it freezes at 0. But water is H2O. Water is 2 hydrogens and an oxygen. It has a definite definition. But if you went into a restaurant and you asked for a silica cylinder containing approximately 20 moles of dihydrogen oxide supersaturated with CO2, you'd get a blank stare. Nobody would know what you meant. So definitions are context dependent. So being context dependent, we go back to this flowchart. It totally depends on the context where we're looking for these features of life, on how we interpret them. So maybe we just don't have the framework yet to define life. How would you define water before knowledge of the periodic table? You wouldn't be able to say it was H2O. You wouldn't be able to classify it in those terms. You would not be able to give water a definite definition. So maybe in astrobiology, we are where chemists were before the periodic table. We currently lack a unified framework in which to give life a complete, definite definition. Or maybe life is something that cannot be definite. I like to think of life as a continuum. There is no point where life evolved on Earth. There is no line you can draw between prebiotic chemistry and the first complex organisms. So this is called the probability or the problem of the minimal living system. So when then is music music? I think we'd all agree that that's music. What about this? Or this? Or... So when does music stop becoming music? Or better yet, when does noise become music? So there's a continuum here. It's a process. There's not a definite point. You can't categorize things as alive or not alive. Sure, you can say, okay, a dog is alive and a rock is not. But what about things like a mini virus, this giant complex virus that can have viruses? What about things like spores? What about life as we don't know it? Would we be able to recognize a second genesis of life if life evolved on a different planet in a different way? So instead of trying to look for life itself, we look for the components of life. We try to answer that first question. Is the system habitable? Could life as we know it have started or evolved? So when we send Curiosity out there, we're looking for the components of life. We're looking for the things that could eventually come together to make life. So what do we look for? Where do we go to find these components of life? Well, one of the most recent and most ambitious searches for life is MSL, Mars Science Laboratory, which is currently in Gale crater on Mars. So why an impact crater? Why would you go to an area that's associated with mass destruction of life to search for evidence of life? take credit for, but I can't. It's a heavily edited version of something I found on YouTube. But it does a pretty good job of displaying what we tend to associate meteorite impacts with, the catastrophe. And media has associated impacts with catastrophe as well, and so has science. I mean, we're constantly bombarded with the idea that meteorite impacts are these episodes of mass destruction and extinction. And at first, they're devastating. They sterilize the immediate environment. They've been associated with some of the most dramatic extinctions in Earth's history, such as the Chicxulub event, which is one of the going theories for the extinction of the dinosaurs at the Cretaceous-Jurassic boundary 65 million years ago. So the Chicxulub impact occurred in the Yucatan Peninsula about 65 million years ago, and the meteorite was about the size of Mount Everest. So that's a pretty big chunk of rock. And the crater itself spreads out through the Gulf of Mexico. And this just shows you the difference between the actual crater there, that pinpoint there in the center, and then the local effects. So you'd have thermal radiation or massive fires. You'd have ejecta. You'd have earthquakes and seismic shaking and tsunamis. So the crater itself is very, very tiny compared to the devastation. In fact, a meteorite, the projectile, will only penetrate 1 to 2 times its own diameter. The actual crater is evacuated by shock waves. So impact events are locally destructive. They can have global effects. They can be globally catastrophic if they're large enough, like the Chicxulub impact. So dust from the vapor plume would completely block sunlight for up to half a year. Photosynthesis would stop for up to a year. The food chains would collapse. Temperatures would drop below zero. I mean, the average global temperature today is plus 14. So you can think of what the Earth would look like if the average global temperature was below zero. There'd be toxic sulfuric acids by dust and acid rain for months to years, which would kill any remaining plants and suffocating the animals and destroying the habitats. So there's no doubt that meteorite impact events are globally destructive events. But years and months, that's a snapshot in time. Just to give you an idea of how old the Earth is, at 4.5 billion years old, if you stretch your arms out like this, and if this represents the Earth's history, and the Earth was born right here at the end of my right hand, and us here today is at the end of my left hand, where do you think humans came onto the scene? At what point? Yeah, I could take a nail file and file the tip of my nail, and that would erase all of human history and civilization. So a few years is just a blink of the eye. So if we think of meteorite impacts in geological terms, they have many beneficial effects for biology. So impact structures, when you look at planetary bodies, impact structures are the dominant geological feature in the solar system. They're the only ubiquitous geological feature in the solar system. The impact flux, or the rate at which meteorites were hitting the Earth, was very, very, very high on the early Earth. They also bring a heat source to an otherwise dead and frozen planet. Meteorite impact events also deliver organic molecules and volatiles. There's a lot of theories that suggest that meteorites, such as carbonaceous chondrites like Tagish Lake, actually delivered the building blocks for life to Earth. And any impact into a water-rich target, like Earth or Mars, will generate a hydrothermal system. Microbes love hydrothermal systems. There's hot water and rock and energy and all sorts of things that microbes love and that microbes need to colonize something or to make an environment that wasn't habitable become habitable. So we can think of meteorite events creating these habitats, creating a habitable environment in an otherwise uninhabitable planet, such as perhaps early Earth. So when we look at the Earth, this is somewhat outdated now view of impact sites on Earth. We look at Earth, we don't see very many. In fact, it's only been really in the last 30 or 40 years that impacts have even been recognized on Earth. We look to the Moon and to Mars to study impact craters. It's because impact craters don't look like impact craters on Earth. When we look at Mars, we see craters, lots of them, undoubtedly craters. So why is the terrestrial cratering record look like this and not like that? There's three main reasons. The Earth is a dynamic planet. It's active. The crust is continually being recycled. It's kind of like a conveyor belt. You know, when you're collecting your luggage off of the conveyor belt after a long flight and you don't get there fast enough, it disappears. Well, the crust is like that. At subduction zones, it goes down into the Earth's mantle, and at spreading centers, it's being constantly formed. So the Earth's crust is being recycled, and if we had most of the impacts on Earth occurring, you know, the early Earth's history, a lot of those impacts have been erased. We also have about 70% of the Earth's surface is the ocean. Well, it's difficult to find an impact crater at the bottom of the ocean, and that leads to exploration. You'll notice there aren't a lot of impact sites where we have areas of rainforest or ice sheets. So those are the three main reasons why the terrestrial cratering record is a lot different than the Martian cratering record or the lunar cratering record. So something that I find really, really interesting is this period or this peak of impact cratering activity. This is a time that's affectionately known as the late heavy bombardment. There's a bunch of different models and there's a bunch of different reasons to why this happened, but it was about between 4.2 and 3.8 billion years ago in the Earth's history. Interestingly enough, that's exactly when the earliest evidence of life says life should have arisen. So why would life have started during the most violent and inhospitable point in the Earth's history? Well, maybe life needed that to get started. And this brings us to Curiosity, currently in Gale crater on Mars. So are meteor craters, are impact-generated environments, habitable? Can microbes survive there? Are they good for microbes? So this is a picture of Gale crater, and there's Mount Sharp there in the middle. There's the landing ellipse where Curiosity landed. And there's that possible ancient lake that was just talked about. And the answer is, yeah. There was a paper published in Science not too long ago that I think we found the first habitable environment beyond Earth. Gale crater is a habitable environment. It has everything life needs to survive. That's not to say that there's life there right now, but life as we know it could exist at Gale crater, or could have existed in Gale crater. So we know that meteorite craters or meteorite impact environments are habitable. They create these hydrothermal systems that bring in all sorts of food for the microbes and heat and all sorts of things that microbes love and need to colonize and grow in an environment. So what about the origin of life? How could meteorite impacts be involved in the origin of life? What about concentration mechanism? So we have all of these prebiotic chemicals. If we have this primordial soup, all the ingredients for life mixing around, and life is only going to be created if these things bash into each other enough to create the first prebiotic molecules. Well, the probability of things bashing into each other is going to increase if you can concentrate them into a small area. So what about a lake? If you have a volume, or x cubed, if you concentrate things on the surface of that lake, all of a sudden you're going from x cubed to x squared. So you have a concentration mechanism. Floating in this beaker here is an impact rock. So you can take a solid piece of granite. Anybody can take a chunk of granite and drop it into a beaker of water and it's going to sink, right? But you shock that rock with something like a meteorite event, it's going to completely spongify it. It's going to froth it. It's going to fill it with so many holes that it will float on water. So crater lakes and impactites, or rocks created by a meteorite impact event, can be changed such that they float on water. So now you have a concentration mechanism to concentrate things from a volume to a surface. What about clays? Well, clays have been implicated in the origin of life because they form these templates that organic molecules love to stick to. Clays also replicate. You can think of them as one layer of clay carries the information needed for the second layer of clay to form. And that carries the information for the third layer of clay to form. Sounds a little bit like DNA, doesn't it? Well, we know that clays exist in impact craters. Another thing that happens when an impact occurs is you get impact glass. Well, glass is not very stable, and it weathers to clay very, very quickly. So here we resist using the Chrism and Omega instruments on Mars are detections of clays within a crater. And what about what we know about the origin of life, or the last universal common ancestor, affectionately known as LUCA? Well, from different kinds of reconstructions, we think that the origin of life occurred in a hot environment. So we have all of these impact environments about the same time as life evolved on Earth. And we have this signature of life evolving from a hot environment. So that can kind of mean two things. Maybe they created all of these experimental warm little ponds, all these impact crater lakes and hydrothermal systems, which allowed life to evolve, or maybe it's selected for microbes that really liked hot environments. So there's lots of ways that meteorite impact events can be implicated on the origin of life on Earth. So this is just showing, again, that phase of thermal biology, or these impact hydrothermal systems that are generated. So we know that life loves these black smokers, or these hydrothermal events are these oases of microbial life on an otherwise desolate ocean floor. So we know that hydrothermal systems kind of attract life in an otherwise deserted environment. And impact-generated hydrothermal systems can do exactly the same thing. There on the left is a bug, or an opening, from an impact crater in northern Canada on Devon Island. And this just shows some of those hydrothermal minerals that are forming as a result of this system. And so this phase of thermal biology, as it's been called, is an important recovery phase, or an ecological phase following an impact event. So when we go back to that initial catastrophic destructive event, we're actually creating environments that can be very important for colonization. And we know microbes love hydrothermal vents. Not only do they love hydrothermal systems, but it's a way that they can be preserved. And if we think back to that kind of those three circles, we need to have an origin, we need to have colonization, we need to have preservation. In order to find life, or evidence of life, that life needs to be preserved. So microbes can be completely mineralized. So these are some images of microbes that have been mineralized in hydrothermal systems. And so we've talked about the habitat creation and colonization on Earth. What about other planets? What about Mars? So impact-generated substrates. These are the impactites, everything from glass, that amorphous material that weathers to clay, to those shocked rocks, such as the shocked granite that floats on water. All of those rocks contain elements, and those elements are very attractive to microorganisms. There are microorganisms that eat rocks. That's it. They get all the energy and nutrients they need from extracting certain elements from minerals to survive. So those impact-generated lithologies are actually buffets to microorganisms. And
Can you give us an example?
Sure. So I've been working with a couple of microbes, an iron reducer that will reduce iron and gain energy from that process. There's another bug that I've been looking at lots of pictures of lately called Biomicrosphera that oxidizes sulfur. And it gets all of its energy from the oxidization of sulfur. So these are microbes that are not linked to photosynthesis. They're not linked to a food chain that's fed by the sun. They're linked to a food chain that's fed from the ground, fed from rocks. So a completely different take on primary production. And so here are some endoliths, or microbes that actually live deep inside rocks. So you can see that green band there. That's a shocked gneiss from Devon Island, from that impact crater, the hot and impact structure in northern Canada. And within that green band, living just under the surface, are lots of nice, healthy, happy microorganisms. They're actually protected from the harsh UV radiation living in that little layer. So not only are these maybe useful environments, but they can be protective environments too. They can protect from the harsh conditions. So the surface of Mars is pretty harsh, but there could well be life under the surface, protected from oxidizing radiation, from UV radiation. Here on the right is an image from one of my colleagues, and if you see here, you have this fracture. So this is an electron micrograph, so it's like a microscope image of a shocked gneiss from Houghton, from Devon Island as well. And you can see that the black area, let's see here, around there. So all of those nice little fractures. And if we go to the next time, this is a stain that lights up microorganisms. And there's all sorts of microorganisms nicely living around that fracture system. So we know that impact rocks not only feed microorganisms, but they also protect microorganisms. And here's the feeding. Here's the buffet table. So when a microorganism looks at a complex rock, it's the way you might look at a pizza. You got your vegetables, you got your protein, you got dairy, all sorts of elements, everything that the microbe needs for growth and to survive. So you have also this porosity. Remember that shocked gneiss that can float on water? Well, when you spongify something like that, you get all of these pore spaces that are interconnected. So now you've got sunlight that's able to get through. So maybe you have bugs on Mars that are living under the ground, but in impact areas, if it's a rock that's been affected by a meteorite impact event, maybe sunlight can actually penetrate that rock. So maybe you're protecting against, oxidizing radiation, but you're at that sweet spot where you have just enough light to allow things like photosynthesis to occur, but not enough so that it's damaging. And we see that. We see that in Antarctic ice sheets. We see that in shocked gneisses where you get a sweet spot. That's why they're not right at the surface. There's a place where it lets enough light in for metabolism, but blocks out enough of the harmful stuff. And then you have the glass. So I have a special interest in impact glass. I've been working with actually one thin section of impact glass, about that big, for about 7 years now. And in that impact glass, I found things that look like this. Now remember, looks like is not a very good argument for life. We can't say it looks like life and call it life. And so here we have a material from Earth. So remember, we're expecting life to be there. And it's here on Earth. So I can use all of the tools I want to use to try to figure out what it is. And there's still lots of people out there that say, that is not life. So I've been looking at these things a lot, and I'm trying to show that these are actually biosignatures, that these are little tunnels that microbes have left behind as they're eating their way through the impact glass, just like worm burrows. So I can look at them like this, these little micro tunnels that microorganisms be making. They branch, they bifurcate, they do all the things that we'd expect microbes to do. They coil, they show evidence of avoidance where they change direction to avoid bumping into each other. But we still cannot definitively answer the question, is it life? So the answer to is there life on Mars? I think life at least started to evolve on Mars. Did it get far enough to colonize Mars? I don't know. I don't think we can answer that question. Was there enough of it to be preserved as evidence of life? I'm not sure we can answer that question either. I think we can define different environments on Mars as habitable or uninhabitable. And if we ever get so lucky as to have a sample return mission, we can start looking at that material and really get into the question of, are we seeing evidence of biological processes? And can we answer that question of what is life? Thank you.
Thank you so much. I really enjoyed your talk. That was super. A good synopsis of some current thinking there. We have time for questions, and I'm sure we probably have a boatload. But since I'm up here, I'm going to take the first one. So, actually, I'll have two questions. For the organisms that you investigate that actually live within the strata of the rock, are they dependent on oxygen at all?
It's a good question. So some of them. So that's a very good question. There are two types of microbes: those that need oxygen and those that are killed by oxygen. So we call the first class anaerobes. So they live in an aerobic environment where there is oxygen and they're dependent on oxygen. And we call the other class anaerobes. So they live in environments that are completely devoid of oxygen, and exposure to oxygen will kill them. So they use other compounds as a terminal electron acceptor in their metabolism. So not all life is dependent on oxygen.
Thank you. My next one is a bit more of an opinion. I don't know if you're a betting person or not, but if you were, what would you say the chances of life under the surface of Europa's ice crust is?
Under the surface of the ice crust.
I've got a few bucks. We could place a wager, you know?
I'm not entirely sure we have enough evidence to make an educated guess there, and I think at this point it really would be a guess. Life as we know it and we're familiar with, probably not. Some sort of life under the various definitions of life, yeah, I'd say there'd be some systems there that would fit under some of the current definitions of life. Life really is a collection of chemical processes. And we go back to that continuum, at what point does something become alive or not? I don't think it's appropriate to place that slider on one end of the scale. But yeah, I'm sure something along that continuum would exist or did exist.
So when we drill down in the crust and we've got the little robotic submarine surfing around there, you think it's going to get like, when it turns on its light, something's going to like... I want to be around to see that.
Depending on how much time life has had to evolve in a particular environment and how fast that evolution occurs are not very well understood or constrained, especially on an environment that we don't know a lot about. And we have a lot of trouble interpreting ambiguous evidence for life on Earth. There are a lot of things that we look at on Earth that we can't decide whether it's life or not. And so I think it's going to be pretty impossible to try and answer those questions remotely with the current technology we have. I don't think we're going to be able to look at data sent back to Earth from a Mars rover, sorry, and be able to say definitively one way or another, is it life? I mean, unless it stands up and waves to us, I'm not sure we're going to be able to answer that question.
Thank you. Thank you. Okay, so questions. Brian.
Haley, nice presentation. Thank you very much. Are you also looking at the ethics of astrobiology in terms of, okay, so say you find something there, are you already looking at what are the protocols that should be in place for safeguarding it from us and from itself type of thing?
Yeah, so there's an entire division of NASA that's dedicated to the ethics of astrobiology. It's called the Planetary Protection Protocol. And yes, I think it needs to be there, but it's also one of the most frustrating things about being an astrobiologist. There are regions on Mars that we're pretty sure have all the conditions for life. Things like those RSL, or the recurring slope lineae, areas that are dynamic and active, but we can't go there. They're protected regions. They're actually called Mars Special Regions. We can't send a rover there because they're protected. Unless we can have a bio load less than that of Viking 1, so a bio load, so the best of our ability, we can say that the equipment is sterilized, which is kind of interesting because our life detection limits are not aligned with our ability to sterilize something. So for now, we can't go there. And for now, we can't bring anything back either. So one option that's been proposed is to have a moon-based laboratory where we know nothing, or we think nothing can survive on the moon. So if we bring it there, it's gonna die if it gets out or gets released. It's never gonna come back to Earth. And likewise, we'll have things that go to the moon, but they'll become sterilized because of the environment on the moon. So we don't have to worry as much about contamination. I mean, contamination is a huge thing. If you bring a sample back through the Earth's atmosphere and then it lands in the middle of the ocean or the middle of the desert, are you ever going to be 100% sure that it's not earthly contamination? So these are a lot of questions that are currently being asked and addressed, and there's no right answer. I mean, ethics lags behind science, I think, in pretty much every area, but it is definitely something that is being addressed and looked at.
With reference to the protected zones on Mars, what are some criteria that make it protected? Like, is there any specific examples?
So I'm sure there's a list of specific criteria. I'm not aware of the actual specifics, but the general idea is that if it's an active environment that has evidence for liquid water, current liquid water, it's hands off.
Interesting.
Thank you for the lovely presentation. It was fantastic. I just wanted to know, you mentioned that you were studying iron-eating bacteria. Mm-hmm. Is it by any chance, do you know, related to the bacteria that is consuming the Titanic, leaving behind all the rusticles?
So I don't know the specific microbes. I'm not familiar with the specific microbes that are actually eating the Titanic. But I would take a pretty good guess that yes, they are iron metabolizing microbes. They're probably anaerobic, or the ones that live in areas where there's no oxygen that are involved. And the microbes that I'm working with would, yes, be related to those microbes. But I couldn't tell you exactly how they're related or if they're the same microbes.
I was wondering with the footprint that it leaves behind, being rusticles, some of the microorganisms that are existing in rocks, has there been any evidence of chemical changes in the rocks where organisms are suspected to show that there has been consumption of some bit and generation of smaller compounds?
Yes, so that's a good question. That's exactly what my postdoc is involved in. So the question was, is there chemical evidence left behind in the rock once microbes have finished eating it? Does that sum up your question? So yes. So just like us, what comes out is different than what goes in. The salad doesn't look the same.
It just doesn't. And the same is with microorganisms. What they leave behind changes. So if you have a rock that starts out with, let's say, start out with a rock that has iron and sulfur in it. And if the microbes only like the iron, you'll see a change in the ratio of iron and sulfur. And if that change is not expected due to the current chemical processes of the environment where the rock is, meaning that what we see is out of equilibrium with what we would expect, then we need some other mechanism to explain that change. And on Earth, that other mechanism that we study is biological activity. So the specific changes that I'm looking at are the changes in iron. So iron can exist in different oxidation states. You can have iron 2+ or iron 3+. So if you have your ferrous iron or your ferric iron. Microbes like to do that conversion. They like to take ferric iron and make it ferrous, or vice versa. And if that happens in an environment where we wouldn't necessarily expect that change to occur, then it's likely that that change was facilitated by microbial metabolism. And we can actually measure that change. So I go to the synchrotron, or the accelerator up in Saskatoon, and I look at the ratio of iron 2 and iron 3 in a substrate that's been eaten by microbes. And I look at those changes and I say, okay, are these changes consistent with iron metabolism? Are they unexpected given the current chemical conditions? And are they recognizable? Are they in patterns that are suggestive of microbes?
Chuck?
Kind of a multiple question. Your impact glass, which glass was it? And have you thought of looking at impact melt versus lava to see the difference?
Yes. So that's from the RASC impact structure in south-central Germany. So it's about a 16 million year old, 24-kilometer diameter crater that occurred into a shallow sea. So the target was some layers of sediment over top of a granitic basement, much like the Canadian Shield. And the glass itself was the bottom layer, the granite. So the protolith for the glass is the granite material. And what happened is the granite was melted and then instantly quenched once the shock wave passed through. And so you have that quenching, and so you have a very chemically complex lithic or rock glass. Actually, I'm setting up some experiments right now that compare the melt, the impact glass, with volcanic basaltic glass. And basalt glass is pretty attractive to microorganisms. It contains a lot of iron, among other things, but it's kind of chemically bland. There aren't very many ways to get melt on the Earth. I mean, a common misconception is that there's magma under the Earth's crust. It's just not true. It's crystalline rock. You only get melt in very, very specific locations. And you only get melt in very specific ways. And all of those ways are due to a series of chemical processes which chemically change the rock as it evolves into a melt. So where you get melt on the Earth kind of tells you what chemistry it's going to be, whether it's going to be basaltic or granitic or whatnot. And so you have very chemically constrained and restricted rock melts and glasses. In contrast, impact melts are very chemically heterogeneous. They're very chemically complex because you don't have any of those melting processes that constrain the melting on the Earth, when as such as impact is instantaneous melting. So whatever was there gets melted and gets instantly quenched. So you get, beautiful things like these skeletal crystallites and all sorts of things that wouldn't be there had the rock been melted through common geological processes. So I'm setting up an experiment to see if rocks like impact glass better than volcanic glass. I'm having a little bit of trouble deciding what type of volcanic glass to use, what would be the best comparison, but it's certainly an area of interest.
Haley, I'd like to know, what is the most important consequence of finding life outside the Earth? I know that's a big question, but why is that important to us? How will that impact us when we do find life outside the Earth? We haven't found a speck yet. So when we do, if we do, why is that important?
I think from a philosophical point of view, it comes back to loneliness. We're social creatures. We don't like being alone. And are you guys all familiar with the pale blue dot image? You know, when you've got basically the Earth in a sunbeam. It's just a speck in there. And the first images that were taken of the Earth from the moon, that kind of started the environmental movement, because all of a sudden the Earth was this fragile object in the vastness of space. And it shows just how fragile and ephemeral we are. I like to liken it to being on an airplane, actually. When you're on the ground and you look at an airplane passing overhead, you often don't think about it very much. It's an airplane. It's this tiny little thing in the air that you might see for a few seconds. But when you're a passenger on that airplane, it's your entire world. And so that's kind of how I think our viewpoint changed when we saw the Earth from the moon for the first time. And so finding life elsewhere, finding life somewhere else, I think it just goes back to to human nature, that we don't like being alone in it, and it makes it seem just a little bit less frightening, just a little bit less all or nothing. I don't quite know how to put that into words, but I think that would probably be one of the biggest impacts of finding life outside of the Earth, is that we're no longer alone. We're no longer just that speck of dust floating in a sunbeam.
Excellent. Thank you so much. I'm going to have to, just looking at our time, I'm going to have to stop our Q&A at this point in time. I'm really hoping that you'll be around for the break, and perhaps Haley can take some of your questions, and perhaps for a little time afterwards. I don't know how much time you do have. But I want to thank you again for a fascinating talk. I love that. And we have something for you. Mr. LeMay, are you around? I learned of this, and I thought this was very appropriate given some of the current theories and thoughts around panspermia and the possible propagation of life from world to world. So Eric is one of our best astro imagers in the club, and Eric, would you like to just say a few words as to what it is you're presenting?
So Haley, I'd like to, on behalf of the RASC, present you a picture that I took of Comet Lovejoy. This was taken in late January with my telescope. It's a 2-hour exposure. So here it is. I'd also like to present you with an annual calendar as well, too, on behalf of the
Thank you.
Thank you. I think we're going to try to talk her into joining the center, too, but that's afterwards. Okay. Thank you again so much, and hopefully we're going to get you back at some point in time, and you can give us updates on your findings, especially if we find something interesting in Gale Crater. So thank you again, Haley, and much appreciated. Yeah, I think so. Yeah, give people a chance to stretch there. So, I see that we're running well into our time. So we're going to take a bit of a break here. 10 minutes, I think. Have we got 10 minutes? Okay, so I want you to stretch your legs there and just breathe a little bit. Washrooms are on your way in from the outside there. I'm not sure where there are others. I'm sure there are others in the complex. Sorry, I'm totally unfamiliar with this place. But we'll see you back. We'll see you back right at 9:30. Okay? Oh yes, and if you haven't gotten your door prize tickets, come on down. We've got a number of cool things to hand out tonight. Okay? See you in a few. All right, well, welcome back, everybody. Hope you had a chance to stretch your legs and grab some air. I'm just going to review a couple of slides that I went through a little bit quickly, and we had some questions during the break because of the high number of people here that haven't been here before. So I just wanted to take a bit of a breather and tell you something about the memberships or the benefits of the memberships in the RASC. I mentioned the number of centers that we have centers across the country, but for our center here specifically, we have some interesting facets that as members you can take advantage of. One of the interesting aspects is we have the Ted Bean Loan Library, where we can actually lend out telescopes. This is a great thing to do if you don't own a telescope specifically. Telescopes, once you get into this hobby, as the seasoned members here will tell you, they can be quite expensive, right? And so if you're at a point where you're deciding, yes, you want a telescope, you kind of want to know what it is you want, because there are different telescopes for different applications, be it imaging, be it planetary, be it deep sky, visual. So it's always a good idea to come out and talk to people that use different telescopes, get an idea of what they can do, what they can't do, and to help you with that, then we also will loan you telescopes free of charge. Free of charge still? Or is there?
There's a small fee.
Oh, there is a small fee. Handling, yes. But it's very nominal, and it's a great way to gather some experience on using those telescopes before you make a larger financial commitment on your own. So that is something that is available to the members. We also have a book library. Unfortunately, that is not available at the moment because of the transition that we're making from the Museum of Science and Technology. Our library is kind of locked up in the museum. And
But we have good reason to expect the library will be available at the next meeting at the Aviation Museum.
Excellent.
It's being
He
moved to the
said
next
positively.
week. Sorry?
He said positively.
Probably, I think I said. Quite likely.
If not, we'll organize a little night off and get them ourselves, you know. Volunteers? I know some of you here would volunteer for that job. So.
As we speak, all of our books are being treated by the conservation people to make sure they have no mold on them.
Ah. Well, that's comforting. Are they dusting them for asbestos too? I hope so.
We were just a little low down on the list of their priorities, so they're only just getting to us now.
Yeah, they had to dismantle the rocket first, unfortunately.
I was waiting for him to blow it up.
I wanted to buy the damn thing and put it in my backyard. Man, what a waste. Anyway, so long story short, when we do get our books back, that is another thing that is available for members is our library. We have quite a number of books, and Estelle is our guardian of the vault in that sense, and you can talk to her about. Are you here today, Estelle? Yes, there you are. I thought I saw you around. So yeah, hopefully next month we'll have that up and rolling. And another benefit is the FLO. Now, the Fred Lossing Observatory is located in the Almont area at the Mill of Kintail Conservation Area. We have a 16-inch telescope out there that is available for members to use. There is a slight fee for that, key fee and such to gain access to the property and help us to maintain it, because we do plow the road in the winter. We do maintenance work on it, and it's a wonderful facility, especially for those of you that live in the city. The difference in the skies between the city and what's out at FLO is quite pronounced. So if you're a hunter of faint and fuzzy deep sky objects, yeah, you want to park out there sometime. And members are also invited to bring their own equipment if they have it. Often in the nicer weather, we have quite a gathering out there, and again, you can share experiences with each other, look through each other's telescopes, and again, once you have training, we will let you use the 16-inch scope. I do have an announcement to that effect. I think I'll save that to the end there, or with the rest of them. Concerning the FLO training?
Coming.
Yeah, okay.
Later.
Later on. Okay, so yeah, we'll have an announcement to follow on that. So again, just some of the benefits of membership. There are a number of other benefits as well, including an annual subscription to Sky News Magazine. You get the Observer's Handbook as well, which has been for decades really a go-to reference for astronomers across the world. It's one of the jewels in fact in the RASC's crown. This is a publication that's put out annually, a couple of hundred pages, very detailed information about what's happening in the sky on a month-to-month basis, plus a whole pile of very detailed information, lists, maps, tables on virtually everything that you can see in the night sky. So a really nice go-to reference. Even in this day of the internet and Google, I still use that religiously because I trust the information on there. It's been reviewed many times. It's not something that is of questionable origin there. So again, you get that free with your membership. So I think I've pretty much covered the bases there. Is there anything I've left out?
Sorry, we have a problem. I'm the only one who knows it, but that's not the slide that's on my computer that we're supposed to be showing right now.
Oh.
The screens are frozen.
Really?
Imagine, if you will.
Hopefully that might...
That's the one we wanted.
That's the one.
So computer in one, there was no input detected.
Now we have a framework.
Thank you. Now
Oh, there we go. Thank you. I knew there was more. All right. So in terms,
There's more.
there's more. So in terms of the price of membership, there's a breakdown there. A regular membership, an individual membership is $72 per annum, bargain at the price. We have also family memberships available so that you can get a bit of a break on enrolling multiple members of your family into the club. And we have a youth membership at a discounted price for students under 21 and under 25. In fact, if you are a student with a registered organization. So, yeah, are we good? Yeah. All right. So. Again, I encourage you, those of you that are new, I hope you've enjoyed our meeting tonight. It's not over yet. We still have door prizes. And, but I encourage you to think about joining us. It's a wonderful club. If you're at all interested in astronomy, you'll soon come to realize there's a wealth of resources in this room, people that are of like mind and will love to talk to you about the things they do in astronomy, the equipment, the imaging, or like you and just have a lot of questions about astronomy. So I encourage you to join. So again, one of our regular segments here is that we like to showcase images taken by members of the club every month. I know it's been very cold out, yes, but there are diehards among us that go out nevertheless and test the limits of their skin and their equipment. And so we have some of those to show you. And the first one is from Stephen McIntyre, who, yes?
Can I just interrupt and
Absolutely.
excuse me everyone for shouting for a moment, but can I shout out to Matt up in the AV room to now we're doing astro images to bring the lights way down?
A wonderful idea, including these.
More so on the screens, yeah?
Yeah.
You can keep going down.
Oh yeah, much better. That's much better.
Yay, thank you.
Yeah, much better. All right. Stephen isn't with us tonight, but so I'll talk to his. Obviously, for those of you that have kept your eyes open, we have had some clear nights in the last couple of weeks, and we were fortunate enough to on the night of February the 20th, the Moon, Mars, and Venus were doing a really nice conjunction in the western sky, and Stephen has sent us that image of that conjunction event. Nicely composed too, if you're watching, Stephen, nicely composed too with the trees, and that gives it a sense of perspective. So well done, Stephen. Oh, yes. And we have another one from Stephen here showing what we're looking at. It's interesting. I don't know how many of you noticed the moon tonight on your way in. Did you see the moon just starting to rise? You all heard of the super moons, right? Today is a mini moon. Our full moon here is a is an apogee moon, where the full moon phase occurs near the apogee, or the furthest point that the moon has in its orbit around the Earth there, as opposed to the supermoon, which occurs near the perigee point of that orbit. So there is a substantial difference that seasoned observers will notice, and even people that aren't used to looking at it, when we get a supermoon up in the sky, and it's a clear night when it's high in the sky, it's very bright. You can typically read a newspaper by it, if people still do such things. And but with a mini moon, you notice that it's not nearly as bright, because it is farther away, and it is from our point of view, it is subtending a much smaller portion of the sky there. So the illumination isn't nearly as great, but a good comparison from Stephen. So thank you again.
I propose we call it a supramoon.
Supramoon. Yeah, we could do that. We could do that. So next up is Janet. Janet, are you with us? Yes, you are.
I can't see.
Don't fall. There we go.
I can do the usher thing here.
Would you?
Yeah.
Do you do popcorn too? No?
Can I have a light here?
Absolutely.
I don't mind if they.
Okay, yeah.
I've got
Go ahead,
these.
good pointer. Okay, if you can drop the lights a little bit there, but yeah, leave us just a bit to read with the notes there. How's that?
Okay, yeah, that's good, thanks. Unlike Paul and the rest of the people on this list, I'm not a diehard for the cold. I went to Cuba to get my images, as you can see.
You're just smarter.
So this one I like to call the Cayo Santa Maria Cuba Beach Conjunction. And what you're looking at here is really the east-west axis of the sky, with Jupiter there at the top, and then the arm of the Milky Way there, and the moon, of course, and the Venus and Mars together. And I was trying to think of some clever way that I could enlarge that section, but I thought rather than doing that, I would just show you the next image, please. So this was taken same night, February 20th, at around 7 o'clock at night. It was a 1-second shot, ISO 1000 f4, using my 24 to 105 millimeter zoom lens, and I was at 105 millimeters, and same conjunction that Stephen got a hold of. I was able to see it in Santa Maria in Cuba. Thank you.
Thank you, Janet. No frostbite in your fingertips. All right, this next one is sent to us by Mike Wirths. Mike is also a resident currently of warmer climes still, but looking to come back to Canada, hopefully in the summer. He has sent us this amazing shot of crater Theophilus. He's using a new type of camera that gives him an extremely tight, high frame rate. So he can freeze images, very, very short images, and it's a very sensitive camera. Freezing the images and getting that exposure time down as short as possible is one of the significant ways we try to do lunar and planetary imaging, because it freezes the turbulent motion of the Earth's atmosphere. And I had a look at this. I saw this image, and I mean, I've seen a lot of images of Theophilus, but you know what? I zoomed into this, and I kept zooming into it. Fortunately, he sent us the full res image there, and as far as I kept zooming in, I'm seeing smaller and smaller craters, and I'm going like, holy smokes! Like he's down to like I don't know, probably craters on the order of 300 meters across, 400 meters across. It's very impressive. When like this, the full scale image is nice, but it really doesn't do it justice. When you zoom in on that central peak, and I don't know if we can do that, Chris, or anything around the rim there, it's remarkable.
Paul, did he send any specs? Shutter speed, things like that?
I think there were some available. Hang on a second. I can't mess with the slide here because Chris is messing with it. The other way, your other zoom.
I'm doing the other one. Mike, if you're watching, good job.
Yeah, excellent job, Mike, as always. They're very, very impressive there. Oh, yeah. And even still, I mean, like I was zooming in. I was zooming in like little areas around the plane here and in around the central.
For that, show us the other area.
Sorry,
Like
come again?
laser pointer, he's on this side.
Oh, okay. Yes, I was zooming in around the plains here. You can see some of the small craterlets there, and in around the central peak, and there's just also the terraces in the crater walls there. Just stunning, the amount of detail. Like I looked at this and I thought, this is comparable to some of the lunar reconnaissance orbiter images that I've seen in some of the images from the Japanese Selene orbiter. So very, very impressive work, Mike, and thank you very much for sending that to us. You can tell Mike likes his warm climates there. So he also sent us this marvelous picture of a close-up of the sun's surface, photo surface at all, and a very long dark filament running across that surface. So again, high resolution, very impressive work there. Thanks, Mike. All right, Stephen Montgomery, come on up.
I was one of the people who went out when it was cold. This was back actually in January, it's minus 22, and it's out. Camera on a tripod, nothing's guided. Go to manual, keep clicking until you get an exposure you like. Next. So again, the comment up in the sort of top to the right, you realize you've got it when you found the greenish object in the picture, so I thought I did all right. Next, please. And then I went, the problem when you're sort of guessing through your camera, you actually have to take and try to zoom in after the picture to see if you've got it. So once you find it, you can sort of keep a track of it. Next. And then I went from like a 200 millimeter lens to 300 and then to a telescope for a moment. And next, please.
Next.
Yeah. That was the same night as the others. We got the two together and then the three. And I believe I have one more. Different night, too late to get all three, but I did manage to catch an airplane. There.
That was Janet.
Is that his last one? Yeah. Okay. Thank you, Stephen. Thank you. Rick has some marvelous images for us. Come on up, Rick. And again, if we can drop the lights there. Thank you.
Okay, so I started off, well, for this evening, we'll start off with some of the stuff that doesn't change. One of the nice things about the sky is that a lot of this stuff stays the same all the time. So you can go back and look at it, or you can look at it in a different scope, stuff like that. So a couple of months ago in Kingston Center, we did a big meeting on barn door trackers, how they work, how to build them, stuff like that. And some people were asking, can you actually shoot digital camera on a barn door tracker? Well, of course you can. So this is a shot of Orion. This is I think it was 3 60-second exposures and 5 120-second exposures at ISO 3200 on a barn door tracker. Let's see, the top button is...
Rick?
Yep.
Can you use the screen, please?
Okay, great. So what you can see, of course, it's Orion, M42 in the middle, the belt. You can actually, this is a 18 to 50 millimeter lens at 46 millimeters. You can see the horse head in there. You're beginning to see Barnard's Loop here. There's another big nebulosity up there. I can't remember its names. So it's really, this is another thing here that I noticed that I don't think I've ever seen anybody else photograph before, specifically as a target. So it's something I'm going to have to go back and look for, do some more research on it, find out what it is. So that's the overall of the constellation, and of course there's a huge amount of nebulosity through this. This could deal with hours of exposure, and maybe I'll try and get some later. Oops, wrong button. The other way? No? Are we getting, give me a next, Chris. Okay, so M42 in the center. This is through 400 millimeter focal length refractor, Canon 60DA. I don't know what the exposure was. ISO 800. Oh yeah, this is actually kind of complicated because the central portions of the nebula are so extremely bright compared to the faint parts out here. I actually have 22 15-second exposures that only show the central part, 28 60-second exposures which show most of the nebulosity, and then 9 4-minute exposures that get a lot of the fainter stuff. And I could, again, go a lot deeper than that yet. And then I just basically combine them all in Photoshop and just erase the overexposed parts to show the parts from the brighter images.
That's really nice, Rick.
Thanks.
That's the nicest composite I think I've seen.
Yeah, ditto.
Oh, thank you. If you zoom in close, you can actually resolve the trapezium on the original. So that was kind of nice.
That's the picture I've been trying to make for a few years.
All right.
I'm
Keep at it.
serious. I haven't been able to pull that one off yet.
So next, off to the left of Orion, in Monoceros, is the Rosette Nebula. This is one of the classic bright nebulosities. The cluster in the middle, NGC 2264, is quite apparent. A lot of this can be seen in a telescope, but it is fairly faint. Much better in dark skies and with a nebula filter. And so that's 64 minutes total exposure.
Hey, Rick,
Yeah.
a lot of people have told me when they look at this image that they also see the skull. I don't know if anyone in the audience can see that, but sorry for ruining it.
Yeah.
Oh, absolutely.
Yeah, that's interesting. Now, just above this, next is an area. This is only actually half of the area. I have another image over here that I haven't had time to process yet. But this is what has come to be known as the Phosphor Nebula because of Robert Gendler's very, very deep pictures of it. But right here, you can see this bright star, and then there's a little triangular cluster here, which looks like an upside-down Christmas tree, and it's in fact called the Christmas tree cluster. I was very interested to see this here, because I don't recall whether I've ever looked at it in a telescope, but it shows, it's called Trumpler 5, very minor little cluster, hardly shows up on like the planetarium programs. There's a few stars in the area, and then you get an exposure like this, and it's like, wow, there's a lot of stars. I mean, there must be, hundreds, maybe even 1,000 stars in there. So that's very exciting. Oh. Okay. Yeah, so lots of interesting dark nebulae around in the area, probably star-forming regions and stuff. Next. This shot was actually shot by my daughter, so it isn't mine. We were coming out visiting her fiancé's parents for dinner, and at the end of the evening we're all getting out in the car. And, oh, nice halo. Wish I had my camera. Well, she had her camera. So she did 2 handheld shots, basically on program mode, of the moon with the halo. And it was only after we got the pictures back. You can see this is the usual halo that you often see around the sun or the moon when there's high cirrus cloud. But there's this additional halo in here. And I don't know if I've ever seen that before. And I went online and researched, and I only found one reference to it. It's a 9.9 degree halo, which is actually very rare. They're hardly ever seen. So this is actually a composite of two pictures mosaicked together. Next, we're into the transition, the transient stuff now. So this, I was out, this was the conjunction of Venus and Mercury back a month and a half ago or so. And I've taken so many pictures of these. I thought maybe I'll take a few hundred pictures of this one. So I put it on time lapse and then just collected it all into a video so we can actually watch the two set. Can you see an airplane go by there? Okay. Next. Well, this is the one that seems to be the popular subject of the night, of course. Mars, Venus, and the Moon. So this is a wide angle. These are basically all from my dock, facing west. So some guy out over on the point across from us has all his lights on all the time. I don't know why, but anyway. So a wide angle view. The next is a later view as it was getting darker. I was down there for close to an hour shooting in a stiff wind out of the west right into my face at about -25. And
20 in Cuba.
yeah, thank you. I was saying that's exactly it. I was saying applause for the photographs and for the holiday stats, yeah. In the middle between these two pictures, next, I ran upstairs and actually put the camera on a little 480 millimeter, 80 millimeter f6 refractor that I've got, and I had to actually shoot through some trees. But you do get a good view of the earth shine. Finally, the big thing for the winter next was Comet Lovejoy. This was on, I think, the 13th of January, ISO 800, and 4.5 hours of exposure, again with the Canon 60DA. This one, as Eric was mentioning last month in his photograph, you align all the images on the comet so the stars all trail and disappear. Then you take all the images, you align them all on the stars. The comet blurs out, but then you can use Photoshop to select all the stars and erase the stars. Then that gives you an image of only the blurred comet, so you subtract that image from the blurred comet image, you end up with just the stars. Then you add on the image of just the comet, and that's what you get.
So you use the same technique as Eric?
Essentially, yeah. The Deep Sky Stacker will supposedly do this all, and occasionally it will actually do it correctly. You can just hand it all the images. You actually have to go through each image and point, here's the comet, here's the comet, here's the comet. And then after 5 or 10 minutes work, it will come up and say, wow, here's a picture, but about 60 or 70% of the time it says, and gives you just garbage. So anyway, that's it. Thank you.
Thank you, Rick. We had one that Mike thought was particularly pretty. I'm sure most of you saw this. If you look at APOD at all, this is taken by Jay Ouellette, and it again shows the conjunction. I'm not sure if Jay is a member of the RASC or not, but Mike was really enamored by this image, and I think it's gorgeous myself. But this is the conjunction as shot over Quebec City. And sorry?
On my birthday.
On your birthday.
It was published on my birthday. It was taken on the 20th.
Here we go, Sylvie.
From my home city, yes.
From your home city. So beautiful shot. I mean, you can he pinned this just right. I'm not sure of the technical details around this one. I'm sure that there was some composition involved here just because of the various light levels. But regardless, it's a beautiful shot showing a substantial amount of detail actually in the Earthshine portion of the moon there, and again Mercury, Mars, and Venus very prominent there, and nicely placed over the over the night lightscape of Quebec City. So a nice job for Jay there. So Jay, if you're watching, good job, good job. All right. Oh yes, I have a few.
We have time for this last guy?
Do we? Yeah. I'm looking for the hook, right? Okay, I couldn't be with you last month at all, so I've got a number of comet images to barrage you with, because this was one of the nicest photogenic comets we've had in our neck of the woods for a while. Made up for a little bit for the bust that was Comet Ison last year. So Lovejoy has been putting on a very nice show. It's been brighter than anticipated. It's still shining nicely in the sky there, up near Cassiopeia. It's in actually Cassiopeia right now. So I just thought I'd show you some of the images that I was able to collect over in January and February. So this one I shot. This was also with a variety of different cameras and different telescopes. This is one you might be interested in, Gordon. This was shot with a 12-inch Dobsonian. Now I teach astrophotography, and I used to teach Dobsonian. You can't really do much deep sky stuff, but the Skywatcher Dobsonian is computerized and tracking, and it enabled me to take 60-second exposures without any trailing on a Dobsonian mount. So yeah, they can be pretty nice. So F5, it's pretty fast, and that's a single 60-second exposure with a Canon 60DA. Okay, next one. That one, yeah, that one I really, I wanted to show you this one. This one was from February the, I can't read my notes here, 15th, I believe. I really like the way this one turned out. This was shot with just a 70 millimeter apo, and it shows a variety of objects there. First, obviously, the comet there. The comet on that night was approximately 8 light minutes from the Earth. But you can see that streak running through almost at 90 degrees to it. That's an iridium satellite passing through that. And it's only several hundred kilometers above, it's orbiting several hundred kilometers above the Earth. This image actually has a lot of perspective to it, because if you look at the next slide, there, that circled star, the brightest one in the image is Hipparcos 9163, about a 6.5 magnitude star, and it's about 1,140 light years away from us. So quite a difference in perspective from the iridium flare to the comet at 8 light minutes to Hipparcos at the Hipparcos star at over 1,100 light years. And last but not least, there's a small galaxy right above the tail there. That's PGC 7197, and it's almost 300 million light years away. So this is one of the things that fascinates me by doing imagery and looking through a telescope, because you are not just looking through space, you're looking backwards through time. It really is a space-time machine. All right, next one. This one was a wide-angle shot. It was way too cold that night to do much else. This was on the 16th. Wind chill was minus 37. And yeah, it was a little bit breezy. So what I did is I just set my 60DA up with the 50 millimeter lens on an Ioptron sky tracking platform. And so this is just a composite of a couple of 60-second images taken at ISO 6400. But what you can see, I wanted to shoot this because the comet is moving into this area. It was just moving into this area of the sky, and there's a lot of really cool stuff up here. I mean, these are the stars of Cassiopeia up here. You can see the Pac-Man Nebula up here. And you can see the Heart and the Soul Nebula up here, and the double cluster in Perseus. So this was on the 16th, and 4 days later, the comet is basically moving on a trajectory like that. 4 days later, it passed very close to Messier 76, the little dumbbell, which I believe is the next slide I have. There we go. So you can see there, again, the comet. That night there was a particular problem with a lot of ice haze in the air, so the tail was rather diminished, but still fairly prominent. It didn't do much to diminish the little dumbbell there. So again, an interesting perspective, because here the comet was about 9 light minutes away or so, and the little dumbbell is about 2,500 light years away. So yeah, we were lucky to get a clear night that night, because it was really only for 2 nights, the 20th and then the 21st, which is this night, where the comet was in very close proximity to the little dumbbell. But the next one I have is my favorite. This one was shot back in January, about a week after the comet made its closest passage to the Earth on its way around the sun. And I've never tried this before, but this is actually taken with my 11-inch telescope. It's a mosaic of 7 images, and that's why the elongated aspect ratio is just shooting along the tail. A mosaic of 7 images. I had to do them fairly quickly because the comet's tail, if you've seen any of the stuff on the web, actually changes. It changes on a fairly short time scaler, so I wanted to get it consistent there. And so I banged off these 7 images at 200 seconds each with a Canon 60 DA and then stitched them together. So yeah, that was certainly for me the best night of imaging on that comet. So very pretty, lots of detail. Thank you. Oh. Thank you. All right. So the last one I have for you, because we've been focusing, I didn't take that picture, but I wish I had actually. Because we've been focusing a lot on stuff in the solar system, and as many of you probably know, I have a penchant for things that are very, very far away. So quasars are amongst the farthest objects that we know. And again, for those of you that don't know, quasars are, there's still a lot of, they're at the forefront of current research, and there's a lot of different theories in that, but the consensus seems to be that these are very young galaxies, very, very far away, and with very highly energetic cores, probably comprising massive black holes, sucking in probably entire planetary systems and other stuff for breakfast, right? So generating a humongous amount of energy. So one of the objects that I'm familiar with and I've been wanting to image for quite a while is a quasar, and it's this next object. Now, I know that's not really as exciting. My comet image was probably better. Oh.
Stop playing. Eric's having problems here, and it's
That's no worries. No worries. So I'll just give you a bit of background on this quasar while Eric is getting it back together. This object is in Draco, and you can go to the next slide, which is my last one. That's it there. Now, I know that's not very profound or anything in appearance, but what's behind it is really cool, because this is the farthest, probably the farthest object that you can see, actually, and I saw this farthest object that you can see with an amateur class telescope. This quasar has an enormous redshift, believed to be moving away from us at 90% the speed of light, and is 12.9 billion light years from Earth. So, because of the expansion of the universe and that light that I managed to capture on that image actually left that quasar 8.6 billion years ago. So some 3.5 billion years before the sun and the Earth were even in existence. Just to give you an idea for how far away this thing really is. And it's about 14.4 magnitude. If you run the numbers on this, if you put the core of that quasar at the same distance of the Orion Nebula, as Rick showed you there, that would be as bright as the sun is in the daytime in our sky. And that's at 1,600 light years from here. So this is an extremely bright object, as you can imagine. For it to be that bright and visible through, I shot that with my 11-inch telescope. And surprisingly short exposure. This is only a stack of 5 200-second exposures. So, and it registered quite nicely there. So it's in Draco. You can certainly Google it there. And for those of you that do have larger scopes, Gordon with the 12-inch, you should be able to pull this in. It's an interesting object just because if you actually see it visually and realize what it is you're looking at, it makes your brain and your eyes tired. Maybe it's the old light, I don't know. It's the photons. But fascinating object to look at. So that was the last of my images there. So thank you. And I did want to put in a shameless plug here because A number of you have asked me about the astrophotography course that I deliver. I have received confirmation from the School of Photographic Arts that the course is scheduled for May. So for those of you that are interested that I haven't notified already, I will be running the astrophotography course at the School of Photographic Arts. You can contact admin@spao.ca if you want to register. That's pretty simple. It's spao.ca, admin@spao.ca. And again, it's 2 full days, May the 9th and, May the 2nd and May the 9th. And then we also do a field session, which I typically conduct out at my place because I have really nice dark skies. So if you're interested, you can also contact me and I can contact SPAO for you there. Let me know if you're interested. We do limit it to about 10 participants just to keep the numbers reasonable. And I'll also be talking to some folks at the Orleans Photo Club in about 2 weeks there, so letting them know about this as well. So if you're at all interested, let me know, or let SPAO know. Thank you. All right, so just a few announcements. Basically, we are starting our public observing sessions shortly. The center is at the Carp Public Library in the parking lot. This is it's in the public where the Diefenbunker site is. For those of you that have heard about that, it's a reasonably nice site. They turn out the lights for us. And there's a nice clear vista out to the west where there's not a lot of light domes from neighboring towns and cities there. So we have our dates set. These dates are as they stand right now, and you can see the primary is the scheduled date with rain alternatives for quite a number of them. Okay, and we do post a go, no-go notification on the website as we approach these dates to let you know whether in fact we do have the weather to support it. Okay, and we are looking for volunteers to help us out. We can typically get quite a turnout at these events of members and non-members at all. So if you're interested in helping out and you have the time, we'd certainly appreciate hearing from you, and we could use your help.
If I could just add one note, we're always looking for volunteers to bring their telescopes. But we're also looking for a few volunteers to help actually organize the events and set them up in advance. So if you're interested in that, please let us know, and particularly let Mike Mogadam know.
Yes. And I'm not Mike Mogadam. All right. March 28th, Earth Hour. So just a reminder that that event is coming up. I don't believe we're planning anything currently with...
We normally celebrate this event at the Science Museum with their telescope. Unfortunately, even though the telescope is fully functional, they're not permitted to have public observing there because they have no washrooms. We're seeing if we can organize something with the museum for this date at some other venue, but we don't know that yet.
Okay, thank you for that. So an interesting observance, though, even if we're not holding any events there. For those of you who have telescopes, depending on how many people participate, you may notice quite a drop in the light levels in the city during that interval. Okay, just some brief club information for those of you that don't know. Some of the names of the people that you want to talk to about certain aspects of the club's operation. For the Fred Lossing Observatory is Ron St. Martin. He's our man to watch over it and keep it well for us. Not sure why Estelle's name is crossed out there.
It's
just because it's not, because I know she's here. Yes, because we're out of commission for a month there, so don't talk to Estelle. Al Scott is not with us tonight. He is the guardian of our telescope loan library. Hopefully he will join us next month. Did Art and Ann set up outside?
Art and Ann are here, but without coffee.
Without coffee, okay. This is a bit of I know. Quit whining, Tim. This is not our usual venue, as you know, so you'll have to bear with us for this month. But you can talk to Art about RASC memberships there. There's our current loan library and some of the goodies that we have in there for your use. All right. Yes, Gordon Webster. Gordon Webster, wave your hand. Right at the back there. We've organized a tour of the Fred Lossing Observatory, and I assume this is open to all our members, whether they've got keys or not, just to come out and have a look?
Yes.
Yes? Okay.
We've got a bunch of people who've registered that they want to do it, and I will be sending out the go, no go.
Okay. So for those that didn't hear that, Gordon said he will be sending out the go, no go depending on the weather, and you're welcome to let Gordon know if you want to come out. If you've never seen the facility, it's a nice place to go and visit. Very very rural, obviously, and you got a chance to see what we're hiding in those buildings, including the 16-inch scope and a warm room. Okay. Yes.
Well, what we're planning is we're planning to do a tour in the late afternoon and then have a star party in the evening, so people can bring their scopes.
Wonderful.
And we'll have the 16-inch going.
Okay, so star party in the evening if it's clear, and bring your own scopes. Wonderful.
That's where we're going to do it. If it's clear, we'll have the tour in the afternoon, star party in the evening.
And do you have an alternative date?
Well, the 14th or the 21st, and our emergency backups would be the Friday night, and we wouldn't have
Okay.
a tour,
But tentatively, those are the 2 dates we should watch for.
yes.
Okay.
And then there's another session booked for April.
For April. Okay. Was there a question regarding that in the back?
Yeah, I just want to know about April, because I'll be away during that time, but I'd love to visit in April if you're having.
April, the weekend of April 10th.
Okay, thanks.
All right. And yes?
We know that.
Yes, we know that one. And telescope clinic? That was I'm sorry.
I sprung this slide on Paul. We had a telescope clinic, one conducted already. It was extremely successful. Requests for additional clinics. There's no date yet, and we're still trying to find a venue for it, but just letting you know that we will be holding more of these, and it's really intended for people who want to come and get assistance from other members on how to set up the scope, how to use it, how to attach cameras to it, and so on. So it's a very hands-on working group with a small number of people.
Wonderful.
Mike, who's organizing it, is really looking for ideas of where he could hold it with a room big enough to spread out lots of telescopes, but that doesn't cost too much money.
This looks like a good spot.
Yeah, the stage is nice and big. Yeah. Okay, so we'll keep you posted there. Michael will undoubtedly keep you posted when he has more details on that. As always, we're going to continue having our post-meeting meeting for those of you that are interested at Perkins Restaurant at Saint Laurent, just north of Ogilvy. And yes, the meeting webcast there. Did we go out live today, Eric?
Yes, we are live.
We are live. Okay, so for those of you that that aren't aware, Eric has been streaming the materials there, especially for our new members there. Our meetings are available up on the web, and this is one of the ways that members in different centers have been tuning in on us as well. It's been very well received, and Eric is in the process of assembling some of the video that he shot, because he's been doing this for a number of years, but we really only started broadcasting this live about a year and change ago. So he's in the process of assembling some of the video that he shot of earlier meetings, and will eventually put that up as well, which I think is
This
wonderful.
slide here shows you all of 2014 online.
That we've got. So yeah, this is from 2014, but I think you go back to what, 2008 or something?
In 2008.
2008. So he's.
And it's all done through YouTube, and the links are all on our website, and then it brings you to YouTube, and you can watch the whole meeting.
So yeah, if you want to dip back into the archives, there interesting stuff, and I really want to thank you for that, Eric. I mean that incentive of yours is amazing. That's why we pay you the big bucks, right? Yeah. Does it all for free on his own time.
Let's double his salary.
Yeah, we'll double his salary. All in favor? Yeah. You just got a major raise. All right. Thank you again, Eric. Much appreciated. For tonight, we had 141 folks, which is very impressive given the change in venue and the fact that it's still cold out. So thank you all for coming out. Our next meeting will be April the 10th. We're skipping 1 week because on April the 3rd it is Good Friday, so I imagine people will have plans for that. And it will be back at the Canadian Aviation and Space Museum.
Can I throw in another caution there? It should be obvious to people at this point with our switch from science to aviation, and we even announced at the last meeting that it would be tonight at aviation, but we're here. It always pays to check the website a few days in advance. For this meeting, I'm thrilled to see you all here. Presumably that means you got an email from me or visited the site, and I hope we didn't have too many people go to aviation, but it really pays these days to double check on the website or on our Facebook page.
Indeed. Thank you, Chris.
In the meantime, thank you, Matt, and to Ashbury for short notice accommodating us and being a pleasure to work with.
Thank you, Matt. All right. Next meeting, just to give you a bit of a preview, we have Tim Cole on celestial navigation. Looking forward to that one, Tim. And we have Jim Thompson talking about the photographic lunar atlas, which is very useful if you're into looking at the moon. A really nice, very nice tool with a wealth of information there. So he's going to give us some data on that as well. Okay, so for last but not least, we're about to give away some door prizes. So
Let's say goodbye to everyone on the web.
yes.
Bye.
Bye.
I'll come back now here.